All right, I'm going to get started with the introductory part of this webinar, and then we will head on into the question and answer portion. But to get us started, thank you for joining. You are in the GCE's Ask the Experts webinar. This is the second of a series of 5 webinars that are associated with our Water in Mine Operations and Slope Stability online professional development course. The topic for this webinar is Water in Mining, Understanding the Conceptual Hydrogeological Model. And this webinar will run for 90 minutes today. After the introduction, we will open up for questions, both pre-submitted and from the live audience. So stay tuned for that. If you're unfamiliar with the Geotechnical Center of Excellence, we are out of the University of Arizona here in Tucson, Arizona. We are an industry-funded and member-led center. We are interdisciplinary, working across industry and academia on collaborative geotechnical research and education, with the main goal of bridging gaps that exist within and between academia, industry, and fields of study. We do research. We have a number of professional development courses beyond the water course. So if you're interested in learning more, send us an email or check out our website. Follow us on LinkedIn. Lots of ways to connect with the GCE. So the course I mentioned that aligns with this webinar and the topics that we'll be discussing today is the Water in Mine Operations and Slope Stability course that's currently in session. Many of our panelists here today are also acting as presenters of content in that course. It is online and on demand. There is a registration link here today. I think one of my team will also put that into the chat for you if you want to learn more about this course. It covers everything from framework and site characterization to today's topic, the conceptual hydrogeological model, into numerical model applications, implementing water control systems, monitoring and reconciliating your design, and then also open pit and underground water management. And our development partners in that course are Pateau Associates, as well as the Large Open Pit Project, which put out the textbook, which we use as a resource for that course in a basis, which is the guidelines for evaluating water in pit slope stability. And I also want to acknowledge our GCE member companies who make webinars like this possible and all of our research and educational projects that the GCE works on. Listed here are all of our board, leadership, and general members, and we want to thank them very much for their support in making webinars like this possible. And now I will introduce the team here today, both the GCE webinar team and our expert panel. So here from the GCE, myself, I'm Jillian Noonan. I am a senior R&D engineer with the GCE, and today I will be your moderator for this webinar. And along with me, I have Julia Potter, who's the director of the GCE. Thank you, Julia, for being here.
Thank you, Jill, and thanks to everybody for being here today. It should be a great discussion.
And also Christian Ortman, who is computing sciences researcher with the GCE. Hello, Christian. Christian is muted, but I know he said he's happy to be here.
Thank you, Jill. Thank you, everyone, for being here today. It should be a great webinar.
Thanks. And Christian and Julia will be helping to assist with gathering and sorting all the questions that are coming in live today. And for our expert panel, who will be addressing your questions, we have first Jeff Beal. Jeff is one of the presenters in our water course and is Global Technical Advisor with Pateau Associates. Always glad to have you on our panel, Jeff.
Thank you, Julian. Welcome, everybody. Hope you enjoy the session.
Also, Jeremy Dowling, who is Hydrogeology Advisor and President of Pateau Associates, as well as a presenter in our water course. Jeremy, glad to have you.
Hi, everyone. Nice to be here.
Simon Scholl, who presents in the water course and is Principal Hydrogeologist with Pateau Associates. Glad to have you here, Simon.
Hey, everybody. Looking forward to some good chats tonight.
Christian Sintolesi. Christian is lead for water for the Americas with Anglo American. Christian, thanks for joining us.
Thanks, Jillian. Hi, everybody. Hope we have a good session and happy to be here.
Lauren Loric is on our panel today. Lauren is Principal Consultant with Itasca Consulting. Lauren, thanks for being here.
Oh, thanks. Good, glad to be here. And these things are always quite interesting. Looking forward to it.
And we have Yos Ryel, who is Vice President for Mine Water Management of North America, as well as Principal Hydrogeologist with Pitot Associates. Thank you so much, Yos, for joining our panel today.
Yeah, thank you, Jillian. Glad to be here and looking forward to the discussion.
Thank you. And lastly, we have John Rupp. John is Principal Hydrogeologist with Pitot Associates. John, thanks for joining our panel.
Yeah, my pleasure. Welcome, everybody, and look forward to speaking with you.
All right, now a bit of information for you, the participants of this webinar. So first of all, this is a webinar, so you are muted and your video is off, but there are ways to communicate with our panel directly today. And that includes both the chat, which some of you have already used to say hello and let us know where you're joining from. But the primary place to put your questions for today is through the Q&A. So the Q&A is a separate button on your control panel. If you have a question, you can enter it at any time during the webinar through the Q&A. And what you'll do is you'll click on that icon and that will pop up a window where you can type in a question. You can view other questions that have been submitted by others. If you see a question that you also would like to have answered, I would ask you to vote for it with a thumbs up. Ones that are rated higher, we will pull first. And you can ask questions anonymously by checking a box in that window. We are recording this webinar and it will be posted to the watercourse site and the GCE's YouTube page. And I will note that this Q&A webinar is intended for educational purposes only. And we do encourage our participants to verify any information before acting on it and to consult directly with a qualified professional if you have specific concerns for your site. And as I mentioned, this webinar aligns with our Water and Mine Operations and Slope Stability course. It aligns with section 2 of that course on the Conceptual Hydrogeological Model, and it is one of a series of 5 webinars that are focused on different topics that are covered in the course. So the specific topics that are related to section 2 are listed here on the screen. So some of the questions you might be asking today that would align with this section or the Conceptual Hydrogeological Model would be understanding the components of a conceptual model, including stratigraphy, structure, recharge, hydraulic properties, groundwater flow paths, surface groundwater interaction, discharge, or influence of the mining operation on site hydrology. So we'll ask you to please focus your questions on these topics that you see here, and then join us for one of the future webinars if you have questions on numerical model applications, implementation of slope depressurization programs, and monitoring and design reconciliation. We will be going through some pre-submitted questions that have come in through either students in the water course or through the form that was accompanying the registration for this webinar. And you are welcome to enter live questions at any point, and we'll be pulling those and also addressing those today. All right, so that concludes my introductory information. 10 minutes, not bad. So now we will begin the question portion of the webinar, and I will invite anyone here as a participant to begin entering your questions through the Q&A. So we'll start off with some pre-submitted questions, and what I will do is I'll read out each question. You'll see it on the screen, and then I will invite our panel to discuss the question. You're able to enter any follow-up comments or questions through the Q&A, and I welcome you to do so. So our first question came in through the survey form, and it is, how do you construct the conceptual hydrogeological model with 2D geological information? So now I will open this question up for the panel for discussion. Would anyone like to start?
Yeah, I guess I'll go. I guess the short answer is you don't or you can't. And I'm not sure wherever you'd get a situation where you just get 2D geological information. But even if you're doing 2D hydrogeological pore pressure model or flow model or a 2D geotechnical model, you still need to look at the wider picture. So I don't know of any real case where you only have 2D hydrological information, unless it's a specific project and somebody's giving you that. But I think the advice is you've got to look at it in 3D because you've got to look at what's going on off section and you've got to look at the wider picture.
Seems pretty straightforward. Any additional comments from the panel?
No,
Jeremy?
I just say, I thought, quite often 2D cross sections are used as a basis to illustrate conceptual models, but usually or always those 2D cross sections are cut through a three-dimensional geologic and hydrogeologic model, and representative information is placed onto those 2D cross sections as a basis to illustrate aspects of the conceptual model. So if the person asking this question has seen some 2D cross sections and is thinking about those, then almost certainly they've been cut through a three-dimensional model to help illustrate aspects of the conceptual model.
Yeah, I mean, I think that's exactly right, Jeremy. I mean, 2D sections are a great way and a standard way and of displaying the data and understanding the situation, but they themselves, as you say, do not constitute a conceptual hydrogeological model.
Yeah, right.
To flip it slightly, a plan map, a geological map, is also a 2D piece of geological information. And on a remote project that we're working on at the moment, whilst the mine site itself had a lot of 3D geological information, the broader area that has a big influence on the regional groundwater flow systems, there was very little three-dimensional data. So we were quite reliant on a 2D map. And that 2D map was mainly based on magnetic surveys rather than actual mapping. So I absolutely echo what Jeff is saying. You need to be getting 3D information, but you also have to do the best with the data that you've got. And the whole point of a conceptual model is that you use as much information as you possibly can to describe the situation, and then you test that, and you test it with boreholes or pumping tests or taking flows from rivers or whatever that might be, and you're testing that conceptual model, and then you refine that conceptual model. The conceptual model is never finished. There's always something new.
Yep, that's a good point, Simon.
And that is a good lead into another question that we received. So with the understanding that there are different scales of the conceptual hydrogeological model, so in the course we overview district scale, mine scale, and slope scale, so from larger to smaller scales. So considering those scales, maybe you might want to talk a little bit about what do they represent, just very quickly for anyone familiar with the different scales, and then how often or how important is it to revisit, update, and verify that your conceptual understanding is still correct for these different sectors or for the conceptual hydrogeological model in general. And I will invite the panel to start. Christian, I see you've unmuted.
Yeah, well, any conceptual model needs to be revisited anytime you have access to new information, or if the system is behaving on a different way as you conceptualize it will behave. Then obviously there's some conceptualization that is wrong, and then you need to revisit and correct it. This would be one of the key fundamentals to update. Also, if you have some change, for example, in relevant climatic conditions, there are some places that, for example, we are seeing a less recharge or more extreme events that are different, then you need to consider how that can impact your flow.
Yeah, and it also depends on the scale that you're working. I mean, if you're working on a particular slope and you're just getting information only for that slope, then you can probably focus on looking at and updating the slope scale model, and if there's no other changes, then potentially the mine scale and the district scale model stay the same. But yeah, it's something that needs to be the big picture needs to be continually updated and revised as data comes in. And is there a time scale to document that? Not really, but in the absence of anything else, probably every couple of years, unless there's any major changes.
I was going to say that in operations, there are typically natural breaks that happen that are tied to slope redesign or instability. So if you have a new instability come online, you might get some new information that will change your slope scale understanding. The mine scale often naturally, there's a new batch of information that comes related to a pushback. The district scale is usually established during feasibility, and then not updated quite as frequently. But if there's any major event or data gathering that happens, then that's a natural time to update.
Yep.
Yeah, and I would also add that it depends on the potential impacts that might be required in terms of the monitoring. So in terms of agency requirements, there could also be some drivers for scheduling that. So in some environments, they require annual updates of numerical models, which would also, drive the update, obviously, of any new data that's available annually. So in some areas, it's required annually to meet agency requirements alone. So that could be a factor.
Yeah, that's true, Yos. I mean, sometimes you're forced into do it.
Yeah.
There's not that many people that do annually, but you're right. There are.
Yeah.
There are a few.
Yeah.
And I do see some follow-up questions coming in through the Q&A, and I'll remind our participants you can enter your questions throughout the webinar related to the current discussion or other questions that are related to the conceptual hydrogeological model at any time throughout the webinar. Any other comments from our panel on this current question before I pull up the next? All right, coming in from our live participants today, what method do you suggest for combining and defining hydrogeological units based on geology, structural data, and especially geotechnical characteristics?
Okay, so maybe I'll go take that one first. So the first thing to look at on the hydrogeological side is the response to hydraulic stresses, i.e., look at the pore pressure data, look at the water level data, and see how the different piezometers and the piezometers installed in different hydrogeological units behave to various stresses. And that's always a good basis to lump them together or to separate them out. And the key features that often split hydrogeological units are structure, lithological boundaries or contacts, or structural boundaries and contacts. So, for instance, a fault zone or a major fault zone will often define the boundary of a hydrogeological unit, as will a lithological contact, and that lithological contact may be steeply dipping or vertical, or it may be horizontal, in which case you then got to your units will be you'll have several units horizontally. So in terms of geotechnical differences, that's really comes down to the smaller scale. So you would look at again the probably the basic fracture frequency information, fracture frequency RMR, to look at how that may behave or how that may differ. But really, again, it comes down to lithology, alteration, and possibly mineralization. And so the hydrology is the wider hydrogeology is typically based, as I say, on piezometers, water levels, and responses. The slope scale, that's when the geotechnical characteristics come in, and probably the key one would be fracture frequency, fracture orientation, and evaluation of the local scale structures, local scale joints and fractures.
Yeah, so I just add to that, Jeff, that so the blockiness is governed by the fracture frequency and RQD. The joint condition also can play a role depending on how the joints are filled or how planar they are, what their characteristics are. So those two things, which are the primary geotechnical characteristics, the blockiness and the joint condition, probably have a role in defining conceptual units for further development.
Yeah, and then there's also the mining induced side of it. So, typically, we define a blast damage zone, which is, the zone where you've got mechanical breakage, which may be anything from 10 meters to, 40 meters, maybe even more. And then you have the zone of relaxation, which is where the stress relief caused from mining causes dilation and causes opening of fractures. So there's those two units, blast damage zone and the zone of relaxation. And then behind that, you've got the zone where there's no mining influence. So there's three zones there. And the blast damage zone and the zone of relaxation, we often combine what we call or what I think you term, Lauren, the excavation damage zone, which has been adopted. But there's really three zones of blast damage, mechanical breakage, zone of relaxation, and then the zone where there's no influence. And structural orientation and joint orientation is really important, because typically the joints open more when they're parallel to the slope. And so where you have joints, structures parallel to the slope, they open up. And if they open up, they potentially lend themselves to water ingress. And if they're perpendicular to the slope, if they're in and out of the wall, they tend to deform, they tend to open up less. And so you get less influence on the water.
To complement, I assume that the person that is asking is referring to a lot of borehole data. So I would recommend always to use composite logs at the same scale, but what is missing here is hydraulics testing that are useful for defining the hydrogeological units and geophysics. And then basically you can have if you're referring to borehole data, then that's a way that you can assess the hydrogeological behavior of the different units.
Yeah, you can almost always enhance a hydrogeologic conceptual model through consulting with different geotechnical data sets for the same sector or domain. So I know Jeff and Lauren have covered off most of them. If there's a fault, a geotechnical fault register for the site, that has often got very useful information that can infer hydrogeologic characteristics. So the thickness and properties of a fault, such as the fill material, presence of gouge, and the continuity that are geotechnically important, will often coincide with hydrogeologic properties of importance, such as barrier or conduit type properties. And then at the smaller scale, the structural fabric, the orientation of structural fabric can sometimes be important to imparting a smaller scale anisotropy into the directions of permeability in the rock mass. So every site is different, and you have to look for the information and interpret it with the hydrogeologic information. But it's almost always the case that the geotechnical data and characterization and the hydro data sets can kind of be mutually enhancing, and they should be used in combination to develop the conceptual models for the site, both the rock mass model, the structural model, and the hydrogeological model. And it's usually very useful to build all of that information into some sort of 3D framework using a code such as Leapfrog, where all of the different data sets can be integrated and evaluated three-dimensionally together, in order to understand all the different three-dimensional relationships between all those different geologic components.
Just going to add, absolutely agree with everything that's been said so far, but I'm also a big fan of trying to keep it simple where you can. So think about what the conceptual model is being used for, and make sure that you apply the level of detail that's required for whatever question that's being asked of it. For example, if it's going into a regional 3D numerical groundwater model, what do you believe that the smallest cell size might be? And that might define how small a resolution you go down to on the layering of certain aspects of your conceptual model. You'd still describe those layers as part of the conceptual model, but you wouldn't necessarily single them out as multiple hydrogeological units. You might lump it as a single hydrogeological unit, but describe it with some sort of anisotropic characteristics. So I like to keep things simple if I possibly can.
Yeah, I think one of the things we say in the course is, I mean, for me personally, the first thing I ever do when I walk onto a mine site is look at as much water level data as I can, piezometers and even open standpipes. I look at that way before any permeability data, because if you see water levels between holes which are similar, it's telling you that you've got connection between those two holes. If you see water levels that are different, it's telling you you haven't got very much flow between those holes. So the first thing to look at is water levels, then add the structural models. And if you can correlate jumps or differences in water level with the structures, then you're getting into having a good definition of the hydrogeological model and the flow system. And I always do that way before I look at any permeability numbers.
Good. All right. For those of you who are maybe just joining us, today we're talking about understanding the conceptual hydrogeological model with our expert panel today. We're accepting questions through the Q&A function and selecting some of those to answer live. Any additional comments on this question before I move on to another from our panel? All right. So this is a question, we touched a little bit on the topic of the excavation damage zone. So I'm going to pull up a question related to that. So during the course, There was a module focused on the excavation damage zone of slopes. Is there an equivalent for underground operations where you see relaxation or concentration of stress around tunnels or stopes? And how may that affect the flow of water?
Okay, I'll give this a go again. So the answer is yes, but on a much different scale, a much smaller scale. So obviously, for most underground tunnels, most stopes are relatively small compared to an open pit. And so the influence of the excavation is less. However, it still can be important. Couple of examples. I'm involved in doing a decline at the moment, and unknown to them, they were mining it parallel to a structure. They started seeing very high rates of convergence in the tunnel, and lo and behold, they then had a slab failure. And it turned out they dilated the fault parallel to the decline, and water got in, and the force of the water had caused the side of the decline to fail. So that's one example. And again, an example I've just been looking at this week. We're doing a dewatering system for a stoping operation which has got quite large spans, and which will ultimately be paste filled. And so, you know, we've asked the geotechs to determine what pore pressure they can stand above the spans to still make them stable. And you know, we would then try and put in the dewatering system to achieve those target spans. And the difficulty with stopes is, one, you don't normally want to get in the stopes and drill them, because you don't normally access is prevented. So you normally have to do it from the side. And secondly, you have to think about the paste fill on the slopes, and you don't want a bunch of water flowing through the stopes that you have to then subsequently paste fill. So I think the answer is yes, but on a different scale.
Yeah, it's a much different scale, and it has all to do with confinement. By the way, the term EDZ, or excavation damage zone, was coined in the nuclear waste isolation industry when they were looking at trying to develop seals and other ways to prevent water from either entering a storage facility or leaving a storage facility. So that term originated with underground excavations.
I knew that, Laura. I was just trying to give you some credit. Come on.
Yeah. So, but it really is a question of confinement. And Jeff talked about in slopes with structures parallel to the slopes. There's almost no confinement, so those things can open up very easily. Structures around tunnels, particularly if they're circular or near circular, very, very difficult for those things to open up very much, because they're so highly confined. You might get an excavation damage zone around a tunnel that's a meter or two, and in slopes we're talking about tens of meters. So that's the difference.
Yeah, this the example I cited of this slab failure because of a structure behind the parallel to the decline. I think it was about 3 meters back, and it was a drill and blast decline, and it was a big decline. So yeah, it opened up about 3 meters back. But yeah, you're right. It's much less.
So talking more on, while we're on the topic of the excavation damage zone, we have a few questions that are within the realm of that topic. So let me see if I can pull another one. So this one came in from Adriana, not anonymous. How do you characterize this nucleus of the damage zone of a major structure in terms of understanding if the changes in pore pressure around the structure could trigger an instability? Are there lab or field tests that could help understand that relationship, the influence of pore pressure on the factor of safety?
So I think the short answer again is piezometers. And so look at your piezometers, and for if so let's say you have a structure, let's say 20 meters behind a pit wall, and if you excavate the pit wall and the pore pressure in that piezometer drops, what it's telling you is probably the structure is dilated, and so the pore pressure drops, but it's also telling you if it drops that there's no recharge getting into that structure, which is you know, then you gotta figure out the wider scale flow system and look at why there's no recharge getting into that structure, and does that situation change, and could that structure then start to form part of the active flow system and create more issues. But I think the answer to the question is piezometers, and I'll let somebody else have a go at it.
I was just going to follow up on that, Jeff. One of the most important things to remember on this concept is that the hydrogeological data overrides the geologic characterization. And there are times when one would think, when you look at the geologic data, if you have ATD or if you have core, that you might get a certain response, but the piezometers will tell you something different. And so it's the pore pressure data that is the bottom line. The other thing is that these structures, the damage zones, they tend to be very heterogeneous. They pin, faults pinch and swell, and there are changes in VDZ based on blast damage and stress relief and those kinds of things. So ultimately, it's a good piezo monitoring network that is the most important.
Yeah, for a major structure in a pit slope design, the only way you could test the relationship between the pore pressure and the factor of safety would be if you had a good understanding of the fault properties, and then you could do a sensitivity-based analysis in a slope stability or deformation model to understand what ranges of pore pressure or changes in pore pressure could change the factor of safety on the fault. But you'd only know whether or not that model was right if the fault actually started moving in the field. If it remained stable, you wouldn't be able to calibrate much.
Yeah, and the question there says lab or field tests. Well, lab tests on a fault are
Right.
difficult or not very satisfying at best. I mean, there's faults always differ along strike and dip. So you do a lab sample at one place and it's going to be different a few meters away probably. And the same with field tests, to try and measure a permeability on a fault and apply that to the whole fault is probably misleading. So, but the piezometers will actually tell you how the fault responds, and therefore they will tell you whether water's getting in or whether it isn't getting in. And again, if you look at there's I'll post on the website. There's a paper that was done in April, and it again really starts to focus on whether the structures are parallel to the slope or perpendicular to the slope. And we see lots and lots of instability where the structures are parallel to the slope because they dilate, water gets in, and then the pressure of the water can start to form a stress on the slope and lead to instability.
You can only develop a relationship between the pore pressures and the factor of safety if the fault was actually moving in the field rate.
Yeah.
Otherwise, you would just be, the only thing you could do would be a theoretical sensitivity-based test with a model.
Yeah.
Which may or may not be right.
Yeah, and often it can be misleading.
Right.
Yeah, so the only lab test I think probably that could be useful would be a fault that has a well-defined nucleus that is some sort of clay material, and a lot of faults have that. So doing tests on that material to try and characterize the strength of it is often useful, but there's no substitute for larger scale information, deformations, slope failures of slopes. But there is one place that I think the lab data could help, and that would be in the characterization of the strength of the fault nucleus.
Yeah, and particularly if it's gouged. Yeah, that's very true, Laura.
And also important the practicality. If it's a major structure, sometimes it may be difficult to put a piezometer right on the structure, but piezometers for sure, if you can put them the different sides of the structure, and then you assess the orientation of the structure against the pit and see if there's any seepage, that can also give you an indication of the behavior if it's difficult to properly characterize the structure itself.
Most structures will pinch and swell over quite small distances, and there's lots of underground situations I've been in where one heading goes through a fault and creates major problems and water inflow. You do an adjacent heading 20, 30, 40 meters away, and you don't even know the fault's there. So they are very, very, or they can be very variable on a local scale.
All right, and just a note for the participants that there are some panelists that have been answering questions in a written form. So if you did submit a question, just make sure you're checking back in the Q&A to see if it has been answered via comment in the Q&A. And I'll also invite any of our panelists here today that if there is a question, we have 12 outstanding questions currently in the Q&A. If there is one that you see that you specifically would like to address, feel free to click on the answer live and we'll see that and we'll make sure to pull it to the front. All right, any other comments on this question from Adriana? All right, I'm going to pull a question that was pre-submitted from one of the participants in the water course regarding realistic pore pressure gradients. What is the highest pore pressure gradient you have ever seen in a mine? And is there any document other than the LOP text that shows examples of high gradients in low permeability media?
So, all right, I'll give that a go if nobody else. So, this is regarding a waste dump and its undrained pressure. But we had a piezometer in the foundation of a waste dump in a clay 4 meters deep. And the static pressure on that piezometer was 2 meters, so 2 meters of head. By the time they constructed a 45-meter high waste dump on top of it, that pressure in that piezometer went from 2 meters to 65 meters, just because of the weight and of the waste rock and the compression of the clay. The geological sequence was 2 meters of sand and then clay below that. So we had a piezometer in the sand. The sand was 2 meters thick. We had a piezometer at about 1.5 meters down in the sand, and we had the piezometer in the clay 4 meters down. And so, as I say, the piezometer in the clay went from 2 meters to 65 meters. The piezometer in the sand didn't change because the load in the clay, when it compressed the sand, it was permeable enough that the water flowed away. So we had the situation where we had two piezometer sensors separated by 2.5 meters with 65 feet of vertical head difference between them. So that's probably the biggest the situation I've ever seen. So, but you do get major core pressure gradients across structures, and I've seen probably 30, 40 meters of head gradient over small distances across structures. In terms of low permeability media, in terms of clay type media, you don't normally get that higher gradient. It's much more, the higher gradients you get are either where you have stress loading or where you have discrete structures. So in a low permeability media, yeah, you get gradients, but they're not normally that high.
It's a good diagnostic tool. You can take a look at vertical gradients, and it can tell you a little bit about what's going on. You know, like Jeff's absolutely right. You get we have situations where you have flow barriers or singularities of some type, recharge, that kind of thing. You can get very, very strong gradients. But in a natural system, if you see the unit gradient, then you know you're in a place where you have some kind of vertical layering, or maybe you're in the Vado zone as you approach the unit gradient of 1. And then if you see fairly low vertical gradients, then you know you're in a lateral flow system. So you can use it as a bit of a diagnostic tool. Very high, you're probably along some barrier. Unit gradient, you're probably you've got water draining freely through the Vado zone, or you're in a Vado zone, or and then when you have, say, lower than 0.5%, then you're starting to get into a natural lateral flow.
Yeah, that's a good point, John. When you have perched water, I guess there's quite a few situations where you can get piezometer at the base of a perch zone or above a flat line structure with quite high pore pressure, and then below the structure or below the contact, there's no pore pressure at all sometimes. So that's a good point.
You can actually get quite strong downward vertical gradients in low permeability rock mass too, especially if there's coupled hydrogeomechanical processes affecting the gradients. So it's not always the case at all that because a media is low permeability and has poor conductivity and poor drainage characteristics that it will contain strong upward hydraulic gradients, or what you might call overpressured conditions. You can quite often get situations in pit slopes where there is a downward gradient due to those coupled hydrogeomechanical processes.
And Jeremy, that leads in well to a question, I believe, on hydromechanical coupling. And I will pull up, that also came from one of our course participants. So just asking a little bit more about relating the fluid to solid and solid to fluid direct coupling with the stability performance of the slope. So this person says they have always associated hydromechanical coupling with the geotechnical impact on the stability of a slope. I find it difficult to understand the impact on stability due to the change in hydraulic properties due to coupling. So could you please relate that coupling with the stability performance of a slope, and just explain that a little bit? And I'll open that not just to Jeremy, but to the panel.
Go on, Lauren.
Go on.
Okay, so
Lauren.
I'll take a crack at that. So in general, the hydromechanical coupling is as described there. It's the impact of a mechanical stress or loading on water pressure is one of the couplings. The other coupling is the impact of water on the mechanical behavior. And that's what we see in slope stability all the time. We just take the water pressure, wherever we get it from, and we put it into a mechanical model. So the coupling is typically that way. And we very, very often do not worry about the mechanical impact on the permeability. But one place where we do that is this zone of relaxation or excavation damage zone or whatever. We don't necessarily measure it directly, but we make an assumption about how that changes. And that is a coupling because we have an unloading of the slope, a de-stressing of it. The structures do tend to open up, so they become more permeable. And so there is that coupling as well. So those things, some of them are more directly considered, and some of them are more indirectly considered. We very seldom have what would be considered a fully hydromechanically coupled model where we're looking at changes in permeability, changes in pore pressure, changes in mechanical stresses. But what we try and do is figure out which of those is the primary behavior and kind of focus on that and make the assumption that the other ones are of secondary importance.
I think, Lauren, the impact of stability due to a change in hydraulic properties due to coupling would be, as we were just talking about now, is when you have a set of joints or joint or slope structure parallel to the slope, it dilates, water can get in. The force of that water then becomes or can become a significant component of the force distribution. So if a structure dilates and you get a head of water behind it, it can lead to instability. I mean, that's a fairly common situation, and particularly it doesn't need to be groundwater either. I think a pretty common situation is dilated structures that receive a little bit of water from the weathered zone, from rainfall, and even from leaky pipes, leaky tanks. If the structures have dilated due to coupling, then and water gets in, then that's a very common reason or a trigger for instability.
Yeah, absolutely. No question about that. But we just make an assumption that that's going to happen. We usually don't do any kind of particular analysis to figure out how wide it's going to be or what is how it changes. We just say, okay, we know that that's going to relax. It has the ability for water to get in there and drive a wedge or a block or a rock mass in front of it. So it's more of a indirect coupling, I guess I would call that, rather than direct coupling.
There's various different types of hydrogeomechanical coupling, I guess, right? So if some near surface structures geomechanically dilate, the structures or the fractures can open a little, and if there's a source of recharge, more water can be introduced, and that can then drive instability. But there's also situations where the rock mass can be extremely impermeable, and as the rock mass is unloaded, there's some volumetric expansion of the rock mass and very small scale dilation of the fractures that are there. And if there's any pore pressure in the rock, it will respond to that fracture dilation by a drop in the pore pressure, so the water in the rock will drop or expand into the new pore spaces, the new porosity that's created by the volumetric expansion. And in that case, the pore pressures have dropped due to a geomechanical change or a change in the geomechanical state of the rock. And in theory, the geotechnical performance of the rock would improve with reduced pore pressure.
So I kind of, don't you think something is
so it could kind of go in different directions in terms of how the changes in the geotechnical state of the rock and the water interact to either improve or reduce the geotechnical performance of the slope.
All right, thanks, Jeremy. Any other thoughts on this question? All right. Okay, so just letting everyone know, we are at 4 o'clock, so that means we have 30 minutes remaining in the webinar. So panelists, if there are any questions that you see outstanding that you want to address, please make sure to click answer live so that we make sure to get to those. In the meantime, I will pull up another question that has been submitted from our live group. Just maybe quickly following up from our discussion we were just having, is there a way to determine the dimensions and distribution of the zone of relaxation?
Okay, I'm going to say the best way of doing it is to look at the piezometers. Quite often, the dilation of fractures, particularly when you get more than about 50 meters behind the slope, is very, very small. And it's very difficult to pick any mechanical differences up in drilling, although there's lots of people tried it. Lots of people have done permeability testing in horizontal holes and sampling in horizontal holes to try and look at the effects of dilation. But probably the most robust system is to look at the piezometers and to see how the piezometers respond to mining the slope. And if you get, as Jeremy says, if you see the piezometers drop when you mine, then the slopes dilating, and you're within the zone of relaxation. But extremely difficult. So first thing again is to probably look at the piezometers. Lauren, you've got a fair bit of experience on this.
Yeah, I was going to say exactly the same thing, that piezometers are the first choice. Try to, again, maybe have a conceptual model of what the damage zone might be, and then see how that fits with some actual measurements. The dimensions and distribution, we'd love to know what those are. We have some very crude understandings about that the depth it's proportional to the depth of mining. So if we're have a pit that's a kilometer deep, the zone of relaxation is much more than a pit that's 100 meters deep. And so we've kind of come to a general understanding that it's about a quarter to a third of the depth of mining, but it's very crude. And the fact of the matter is there's precious little information that actually tells us that. There really is not a good mechanical or conceptual. Well, conceptually we do understand it, but how it actually goes together is much more difficult, because it does relate to connectivity and all kinds of other things. So I would lean most heavily on measurements. and try and relate that to some sort of conceptual understanding of what the depth might be. And it's not the same for all rock masses either. This rule of a quarter to a third of the height depends very much on the characteristics of the rock, how brittle or how ductile it is, how strong it is. Imagine a rock, if it was infinitely strong, it might you might be able to put a pit in that's a kilometer deep and not see much relaxation at all, because maybe there's very, very few fractures in it compared to something which is much weaker and much more jointed. It's going to show a larger zone of relaxation. So
and the orientation of the joints.
Yeah, all that.
If
Yep.
the joint orientation is parallel to the slope,
Yeah.
you're going to get more.
I think there's a few sites that maybe have tried looking at some empirical things. Horizontal drain drilling maybe can somewhat infer rock mass quality at depth, just in terms of the drilling performance. And then there's a few mines, I think, where there are tunnels, old underground mine workings and tunnels close to the pit slopes, where maybe you can see deformation in the tunnels that may be related to the pit slopes.
Yeah, you're right, Jeremy. There are some of those sort of evidences that help, and some of them come from microseismic studies where we have a pit. They've looked at the wave velocity in rock around the pit, and that's part of the support for this, a quarter to a third of the depth. So, for example, at Bingham Canyon years ago, they did they had a microseismic network. They back analyzed it to show that there had to be a zone of lower seismic velocity around the pit, and you can infer that very well that that's a zone of relaxation, because the joints have opened up, the seismic velocity has dropped. And those are probably some of the best sources. There's some studies going on now where they're doing cross-hole seismic monitoring. So rather than trying to do it on a pit scale, they'll measure the seismic velocity between a couple of holes, maybe 50 or 100 meters apart, and then before and after an excavation of a slope. And you can get a much better idea of that. But you then have to relate that seismic velocity to a change in permeability, and that part's missing.
All right, thank you very much for your discussions on this question. Any other comments from the panel before we move along? All right, talking about, I guess, just getting a little bit into numerical modeling. We will be covering that in our next webinar in more detail, but this is relating to having a good understanding of the conceptual hydrogeological model as a precursor to numerical modeling. What prior information needs to be analyzed and monitored to achieve the most realistic numerical modeling possible? And how do you incorporate the A, B, C, D order of fractures? Or when is it not correct to just use an equivalent porous media model?
Well, okay, I'll give it a go. So what prior information needs to be analyzed and monitored? So really the key thing with a numerical model that helps you validate it is if you have some piezometer responses to stress, i.e. long-term pumping trials or excavating the pit, then you can calibrate the model. You can calibrate a transient model to the changes in stress. And so really, it's very difficult to validate a model unless you've got unless you've got variable head data, unless you've got responses of piezometers to some kind of pumping or excavation of the pit. So that's the most important piece of information, is responses of piezometers to stress. So the ABCD fractures, it depends on the scale that you're looking at. Remember that we said in the course, that ABCD model could be on a scale of 10 meters, it could be on a scale of 100 meters. If it's on the scale of 10 meters, you don't really, the models aren't really designed, or very few models are constructed with a grid size less than 10, about 10 meters. So what you would normally do is you would select the A structures and possibly the B structures on a wider scale and incorporate those in an equivalent porous medium model. So incorporate them into an EPM model. And so the final part of the question: when is it not correct just to use an EPM? And up until very recently, I would have said the answer is you should never use a fracture flow model, because it's, for the reasons we've said, it's any fracture is variable over very small distances. Any fault is variable over small distances. So how do you characterize it? So it's very difficult to do that. So most fracture flow models that you see are very, very academic. And so the applications are difficult, and they tend to give misleading results. So for the vast majority of cases, and up until recently, I would have said all cases, you should do an EPCM model and not a fracture flow model. And the case I'm thinking about is a special case we're working on at the moment, where we've got a groundwater temperature of over 100 degrees, and we're using free flow to try and look at the thermal transport of water through the rock mass to see how quickly to look at the groundwater flow and free flow and see how quickly the waters will mix and the waters will cool. And it's a fracture flow situation that we're applying a porous medium model. And the issue is that the temperature component thinks it's a porous medium model, whereas in fact it's a fracture flow model. So the contact with the rock is much greater than the contact will actually be. And so that's a situation where we're not getting enough cooling because the model thinks it's equivalent to porous media that's trying to push the water through all the pore spaces, whereas the actual velocities will be through fractures will be that much greater, and so we'll get more cooling because of that. But that's a special case, and what we're going to do with that is actually just take a fracture flow model and look, not a wider scale model, but we're going to look at some specific simple 2D probably situations, and to try and understand the difference in cooling or in thermal transport between we'll set up a 2D model with an EPCM, and we'll probably set up a 2D fracture flow model, not to look at absolute results, but to look at the difference in cooling between the two models. So that's one very rare example where you might need to look at a fracture flow model.
All right. Any other comments?
Yeah, just a quick one. The data, I mean, you've got to have a good conceptual model, and so you have to look at the data until you've captured the key physical processes. If you don't have those in your model, your numerical model, then it's not going to be realistic. So it's, at a very high level, you've got to look at the data until you understand the conceptual model and you've identified the key physical processes, and then you've incorporated them numerically.
All right. Well, I'm going to bring up the question that will provide an additional challenge to that. So what about in the case where you do not have clear correlation with your hydraulic parameters that you are measuring to make an assessment about hydrogeological units, and how can that impact your characterization?
I guess I'm
Handle that.
trying to understand the questions. How can impact geotechnical?
Yeah, I think how would a geotechnical characterization be impacted if you do not have clear correlation with the hydraulic parameters? I'm reading this as that you're measuring. And what might you do about that situation?
So I guess if there's no clear correlation between the geotech model and the hydraulic parameters, that's often okay. You know, the correlation between the two in most rock masses is results of fracture and joint frequency and fracture and joint orientation, as we've just said. So really, that's the link, is to look at the do some tests in various units, look at the permeability, and then try and relate that to the data you have on RQD or fracture frequency or joint orientation or other geotechnical parameters.
I mean, if you've got geotechnical domains in a pit slope that are weaker or higher risk, creating potential impact to the slope design, limiting the slope design, or are potentially sensitive to pore pressure, then you have to characterize those geotechnical domains with hydrogeologically, right? So install test holes and piezometers and drains or wells, and make sure there's a good understanding of those higher risk geotechnical domains, so that there's a clear understanding of how the pore pressures can be controlled as it's mined.
Yeah.
So I was just trying to think cases where there wasn't a clear correlation, and that may be evidence that there are some other major structures that are actually controlling the hydraulic behavior rather than some sort of link between geotechnical characteristics and hydraulic parameters like permeability. Maybe it's telling us that there's something else that's more important than just the rock mass permeability, for example.
The transient recharge is a good example of that.
Yeah, I mean, you have to interpret all the data sets appropriately too, right? I mean, just because there's a high fracture frequency in a rock mass, it doesn't mean it's permeable. If all those fractures are filled with clay, then it's not permeable. It's impermeable, right? So you have to look at all the available data sets and make sure you have a complete understanding. Same with RQD, right? So if there's a low RQD rock, it could be fractured and permeable in some cases, but it could also be a clay material that's extremely impermeable. So you have to make sure that there's adequate characterization of both the geotechnical parameters and characteristics and the hydraulic parameters, so that you can be confident that you understand how the geotechnical characteristics of the rock affect the hydraulic properties.
We did have a question relating to characterizing the hydraulic properties of faults that are creating compartmentalization with groundwater convection cells. Is it better to consider faults as no flow boundaries or high permeability bodies in the structure's orientation? And
So
Go ahead,
the
Jeff.
vast majority of faults are barriers across their strike. Not all, and there's an example in the course. I'm not sure, it's maybe later in the course, but the vast majority of faults are barriers across strike, and there's 4 reasons for that. One is they offset the stratigraphy. 2 is they potentially have gouge. 3 is that they create altered rock and softer rock around the fault, so the fractures heal. And fourthly, you often get subparallel microfractures either side of the fault. So the water wants to go perpendicular to and not cross the fault. So there's those four reasons which mean that the majority of faults create barriers across their strike. A lot of faults create localized preferential flow along their strike. And so that's a thing to consider also, is that you often get water flow along the structure or along fractures parallel to the structure. But typically that doesn't go on. There's not that many structures which are conduits to flow over very long distances, because most faults pinch and swell, they're offset by other faults and so on. And so the majority of faults, if they do create that enhanced flow along strike, it doesn't go on for forever. It's, typically tens of meters or hundreds of meters rather than kilometers.
Yeah.
Okay, makes sense. I see nodding heads. All right, thank you, Jeff. So just in the last 10 minutes that we have here, I'm going to switch topics a little bit. Firstly, to climate change analysis. So when considering a site-wide hydrogeological study related to mine operations, would the panel think it would be advisable or important to conduct a climate change analysis? This is from Marina.
This has got to have your name on it, Simon.
I was just leaning forward, getting ready for it. Yeah. Yeah, it's not always straightforward, but I think at a very high level, global climate models are still not brilliantly accurate. There's many different global climate models with various different sort of carbon loadings, or that basically you can look at the pathway that you're going to have that's going to affect you. Do we switch globally to renewables very quickly, or do we just keep pumping lots of CO2 into the atmosphere and so on? So there's many different numbers you can pick to look at your climate change analysis. So just the climate models themselves are highly complex, and they're really designed to look at temperature first and foremost, and even things like precipitation aren't always simulated or predicted particularly well in those sorts of models. Take that a step further to something like groundwater, where you're looking at recharge. Now, there's many factors that affect recharge: the intensity of the rainfall, the evaporation, the vegetation that's growing, the ability for that vegetation to grow, and how that might be impacted by climate change. So you've got a huge number of different factors that can affect you. So my opinion tends to be try and keep things simple. If you're looking in the relatively short term, and this is very specifically to do with groundwater I'm talking about now, then on the whole, climate change is not going to really impact groundwater flow in any kind of conceptual or numerical model. If you're looking longer term into something like closure assessments, then certainly there could be an impact. I would say really for a lot of closure studies, you'd be better off looking at a sensible sensitivity analysis to understand the pocket in which your groundwater variations might change, levels, flows, and so on. So maybe pick a slightly wetter, higher recharge type environment versus a drier, lower recharge environment, and just look at a sensitivity rather than trying to do something absolute. So in mine operations, broadly speaking, I personally wouldn't advise it as a general rule, but obviously there will be site specifics for certain conditions on certain sites or certain locations.
Yeah, I think you got to look at what the consequences are, right? If you're in the Arctic and you get global warming, permafrost degrades, you may lose strength in the foundations because of lack of permafrost. You may get enhanced flow because of permafrost. In a wet climate, you may get more intense events, you may get more erosion, you may require higher sumping systems in the pit. So you got to really look at what the implications are and decide whether it's important or not. And a lot of times it may not be that important because it may not have any consequences on what you're doing. But you've got to look at it on a case-by-case basis.
I think in some regions that it's more of a surface water flow question is becoming quite important. So in the Southwest USA, for example, there's a lot more high intensity cloudburst type events, 1 in 100 year, 24-hour storms occur quite frequently, not once every 100 years, but almost every year. And the peak intensity of the storm is much higher in recent years than it used to be, and that can have an important impact on erosion of pit slopes and sort of sudden rapid inundation of mine operating benches, and even contribution to deformation and slope movement. So consideration of those extreme climate events, short-term cloudbursts and surface water flows that can impact pit performance and slope stability is becoming something important, and that's being looked at much more and taken much more seriously now than it was a few years ago, because there've been a lot of upset events that mines have had to deal with in the region. But that's not exactly hydrogeology, that's more a surface water consideration.
Yeah.
Good.
The site one at the moment had a 1 in 100 year 6-hour event last week, and what's good thing about that is it enables them to understand what that did. They've been able to monitor it and understand it. It didn't actually do much damage, but it gives them good empirical data to be able to calibrate larger event models.
So some instances, especially in the Southwest, the average annual rainfall from one year to the next is the same, but the way that the rainfall occurs during the course of the year is different. So you get longer dry periods and then short, very intense bursts of rainfall that are much more destructive, shall we say, or damaging. And that's certainly becoming an important consideration for a lot of sites.
All right, good. I think I'm going to sneak in one more question before we close. And just also looking to sort of the future of developing your conceptual hydrogeological model. What does the panel think about using machine learning or a massive geostatistical data analysis to identify correlations with parameters from other disciplines in order to assign hydraulic properties for their hydro models? Are you seeing this as something that's being done in a reliable way?
Yeah, I think certainly in the geotechnical world, you can, we're seeing machine learning applied to slope stability and analysis of radar trends, for instance, and to try and look at to try and identify radar trends that have happened before, for instance. In the hydro world, it's potentially a little less advanced. I'm not sure you could. I'm not sure it's realistic at this point to use it to assign hydraulic properties. Because of the site-specific nature and the you know, the difficulty of applying one set of data to another, which often doesn't correlate or often isn't relevant. But certainly in terms of trends and monitoring trends, then yeah, it's I was certainly starting to see a lot in the geotechnical world.
Good. We still need our hydrologists to perform their duties.
Yeah, I mean, I think one of the dangers is if it starts to apply to models which are already uncertain, and then you use machine learning, which potentially adds another layer of uncertainty. So I think there's a danger in that.
Yeah, you have to be able to give it some rules.
Yeah.
And so you need the fundamental building block has to be a very good data set. But I mean, you know, we already try to look for correlations between hydrogeologic data sets and other geological or geotechnical data sets to try and enhance the understanding and the conceptual model. So if, you know, machine learning can be used to help enhance correlative analysis, then why not? Provided it's supported by sound data sets and that it's correctly set up with rules that will allow it to provide credible answers.
Makes sense.
But yeah, there aren't too many case examples at the moment, though. It's mostly geotech, as Jeff says.
An area for future research, perhaps, as well.
Yeah.
All right. Well, any last minute comments from our panel on this question before I close the webinar?
No, I think it's certainly a good question to get everybody thinking about it.
Yeah, thank you very much, Adriana. So I want to thank very much the cumulative brain power that has been here today with this amazing panel that we have, including those who had to drop off early, Christian Sintalese and Yos Ryel. I'll let everyone know here that's participating in this webinar that we have another upcoming webinar on August 29th related to water and mining, and that will focus on numerical model applications. I did see some questions coming in today that I think would fit really well into that webinar, so please come back and bring those questions with you to that webinar and that panel. Thank you so much, panel. Thank you, participants, and I appreciate everyone's contributions today. And we'll see you at our next webinar. Thank you.
Thanks all.
Thanks, everybody.
Hope you got something out of it. That's good. Good questions. Thanks. See you next time.
See ya. Bye.
Thanks, everybody. Bye.
Goodbye.